Hey, Calc students, it's Mr. Beck. Today we're going to be talking a little bit about applications of derivatives. We're going to be starting that chapter. Just as a quick refresh of everything that we've done all year, very first thing we did was we talked about limits and different properties of limits, and we used that to establish continuity. We used that to establish vertical asymptotes and limits to infinity for horizontal asymptotes. Then we went into chapter 2 where we used the limit definition to come up with the definition of derivative. And then from that, we went into skill mode where we said, okay, what's the power rule? What's the product rule? What's the quotient rule, chain rule? Implicit differentiation was part of it. And then 2.7 is really kind of that one change where we say, okay, now, I mean, there's still some skill involved in terms of implicit differentiation with respect to time, but where we get to go with it is, hey, let's apply derivatives and see what we can do with it. So in 3.1, we're going to be talking about some of the applications of derivatives. Mainly, we're going to start off with extrema. This word extrema really means extreme values. So what are all of the extreme values on a function? So the extreme values of a function, when we look at those, we're going to be talking about what is the maximum value and what is the minimum value. So if we take a look at this graph right here, we have, okay, what's our maximum value? Our maximum value is going to be 5, and I do prefer you to write it in this way, the absolute max of 5 at x equals 2, absolute min of 1 at x equals 0. The reason why I like to use this kind of terminology has to do with the fact that these functions have meaning. For instance, if you're trying to find the minimum cost, you're not going to say, well, the minimum cost is $300 on the 30th day. You're just really going to say, what is the minimum cost? What is the maximum speed? What is the maximum profit? What's the maximum revenue? What's the minimum, fill in the blank. Whatever our function has to deal with, we always say the dependent variable is going to be the maximum or the extreme value. Then let's take a look at how we're going to define that extreme value. On the extreme value, we say that y value, oops, wrong tool. That y value is going to be the minimum if that y value is smaller or equal to all the other y values on the interval. And then we could use the same thing to say it's a maximum if that y value is going to be bigger or equal to all the other values in the interval. We do call these extrema. Extrema is the plural of extreme. It's the plural of extreme, the extreme values. Anyway, a lot of times we're going to say extrema, and when we say that, there's this word absolute extrema that is kind of built into that statement. Absolute extrema, not to be confused with relative extrema. We'll be talking about those pretty soon. And then one of the mistakes, as I mentioned, is naming the independent variable as the extrema. The extrema here is not 2, that's where it occurs. So, if we take a look at this graph, what we see is there is no extreme value, so there is no maximum, even though it does have a minimum. We look at this graph, we have a maximum, but no minimum. Pretty straightforward when we're taking a look at the graph. So the question comes down to what happens if we don't have a graph? What happens if we just have the equation? What's going on with the equation? Can we be guaranteed that we have extreme values? Well, we can take a look at the graph and say, we're not guaranteed extreme values if we have a discontinuity. So we do see the discontinuity there. In my mind, that means discontinuity is going to be something that's required for an extreme value. If we take a look at this, we can say, okay, we do have continuity on our interval, but we don't have all of our extreme values. So what extreme value don't we have? We don't have a max, and this extreme value would occur at the endpoint. So these two ideas combine into what's called the extreme value theorem, that in order for us to be guaranteed that we have extreme values, what we need is continuity on the closed interval of the function. So basically, think about it, if you have any function that has a beginning and has an end, so any function has a beginning and an end, there has to be an absolute largest value and an absolute smallest value. Kind of common sense on one level, but it's nice to know what are all the conditions that are necessary for us to be guaranteed the extreme value theorem, or the extreme values. That's just continuity on a closed interval. A lot of functions that we worked with are continuous on those intervals, but like anytime we want to use this, we do have to check, do we have continuity? And we've been doing that all year. We've been really starting from the definition of continuity. We've been establishing what functions are continuous, derivatives, were they continuous, were they not continuous, and so on and so forth. Now, let's take a look at this graph that we have right here and say, Okay, we've talked about what absolute extrema are, so what are relative extrema? There is only one absolute max and one absolute min, and those can occur in a variety of places. One of the places they're going to be occurring are where we have relative extrema. So if you notice, I have multiple relative extrema, and that's going to be the case that you can have multiple relative mins. So even if you have like a fourth degree function, I guess that's not fourth, that would be in a seventh degree function. We have lots of different relative extrema that are going on in there. We have three relative maxes, we have three relative mins. So um, sorry, I had somebody knocking at the door, interrupting me. I'm going on. We can have multiple relative extrema, but we only have one absolute extrema. So when it comes to our relative extrema, what do we know about where these relative extrema occur? These relative extrema occur here, here, and here. And those relative extrema occur where we have, and what it looks like, we have slopes of zero. But not every slope of zero is going to give us a relative extrema. If you take a look at that slope, we don't have one. If we take a look at that slope of zero, we don't have one either. So we're going to have to refine our definition of relative extrema a little bit. Let's take a look and say, actually, I have a couple of graphs on here. Let's take a look at this graph. Do we have a relative maximum here? As I take a look and I say, okay, what does it mean to be a relative maximum? So whatever the y value is here, we have a slightly higher y value, and then we have that y value that we previously had and continue on. So the question is that point relatively higher than all of its surrounding points? And that statement that I just made is really kind of the defining feature for how we say relative extrema. First of all, we do have to have a defined value of that z. Hopefully we do. Second of all, we're going to be talking about extrema on an open interval, which means relative extrema are not going to be occurring at the endpoints. So if you look, this is not a relative minimum here because that's an endpoint. So absolute extrema, they could occur at the endpoints. Relative extrema do not occur at the endpoints. Now, yeah, we have an open interval that contains a c value such that, let's look at this and say we have a relative maximum where the y value that we care about is only greater than all of the surrounding y values. So we say we have a relative max if that y value is greater than all the surrounding y values, which kind of makes sense. And it's very similar to what we did for absolute extrema. The difference is absolute extrema included the endpoints, and it also included that if we have like a horizontal line, are all of these relatively greater than all the other ones? And the answer to that is no. Some books do have a definition where you can include that. Our book is not going to be including that. Which, okay. Going back, relative minimum, the y value that we care about is smaller than all the other y values surrounding it. So taking a look at our relative extrema again, going back to a situation maybe like this, the y value that we have here is greater than all the surrounding y values. Now, one of the important aspects is this domain is continuous. So the domain is continuous even though the function is not continuous on that domain. We do have a y value that's greater than the surrounding y values. So that is a relative max. And it turns out that's an absolute max for the graph that we have here. Looking at this graph, we do have an absolute max. We do have a relative max here as well. So this one is going to be an absolute max. It's also a relative max. My handwriting is not always the best sometimes. I do see that we have a relative min. We have a relative max. We have a relative min. We have a relative, we don't have a slope of zero, but we do have a relative max. We're going to talk about that in a moment. But we have no absolute min. And the reason why is because as we take a look on either side of this graph, it goes down to negative infinity. Negative infinity is not a defined value. And since it's not a defined value, we can't say what that absolute minimum value is. So let's kind of recap a little bit where we're at because I want to tie a lot of this stuff together. What we're looking at is our goal is to find extreme values. To find extreme values, we know by the extreme value theorem that we have to have continuity on a closed interval. Those extreme values can occur at two separate places. Those two places that it can occur are where you have a relative or where you have an endpoint. So extreme values will occur a relative and at an endpoint. Relative maxes and mins, we see that those relative maxes and mins tend to occur where the slope is zero, but not always where the slope is zero. And not always, I mean, this is a relative max here, but there is no slope of zero there. So what's going on there? This is a non-differentiable point. And if you look, we have another one of those right here as well. So to summarize, absolute, and let's go ahead and write this down. So absolute will occur at endpoints and relative extrema. And relative extrema will occur where we have horizontal tangents, means slope is zero, or the slope is undefined. But also, very, very importantly, f has to be defined there. So one of the things that we do need to watch out for is that if we say extrema, that means absolute extrema. Relative extrema are going to be defined as relative extrema, or sometimes we do say local extrema. Now, we said that relative extrema are occurring where our slope is zero or undefined. So because that occurs over and over again, we have a special name for that. Special name for that is a critical number. So if f prime is zero or f is not differentiable at that value, then we have what's called a critical number. But it's extremely important that f is defined there. And I do have an example here where if I have f of x equals 1 over x plus 2, we know that f is not defined at x equals -2. Derivative here, the derivative never equals 0 because the numerator never equals 0, and the denominator equals 0 when x equals -2. That's not a critical number because it's not defined on the original function. Now, it does have some special properties that we're going to look at primarily starting next time, but I guess train of thought just got lost. I apologize. So it's going to have some important properties, but it is not known as a critical number. And also, not all critical numbers yield extrema, which we saw right here and right here, where the slope is 0, which means that they are critical numbers, but they don't yield the extrema. So let's take a look at the candidates test. What the candidates test is used for goes back to how am I going to be able to find all of my extreme values? What we're looking at is we're going to be looking at endpoints and relative extrema. Now that we've defined critical numbers, let's come up with this idea of what's called the candidates test. And AB loves using the candidates test, by the way. It was very, very valuable. So what we do is we find all the critical numbers, and then we do have to establish why they're critical numbers. So you're going to see me write this, f prime equals 0 and f prime is undefined at. That's because that's our way of justifying that we have critical numbers. So we're going to find our critical numbers, evaluate the endpoints. The least of those is the minimum, the greatest of these is the maximum. It's short and sweet. So take a look at example number 1 here. One of the things that I did in class with my students was I did a lot of playing with the graphing or with the TI Inspires. With the TI Inspires, I had the students find the derivatives. One of the things that I'm kind of pushing for in this chapter 3 is let's go ahead and find the derivatives using the technology and then kind of explore what's going on based off of the derivatives. Please don't just use your calculator to come up with all your derivatives because you don't want to lose a lot of the skills that you have, and those skills absolutely need to be kept fresh. So you need to know how to take the derivative over and over again, but at the same time, right now we're applying the ideas of the derivative, which is why we're saying, okay, go ahead, let's use the technology to come up with the answers. So in one of my classes, I did go through this as a product rule, and we do get the same thing, ironically. So with that said, we said f prime and f prime equals 0. So now I'm justifying why these are critical numbers. So this is my critical number base. I have critical numbers for these x values. Candidates test is very nice for us to put it in a table form. Do you have to do this? No, but it's very nice if you have there because it looks a little bit more nice. And then go ahead, the max is 81 at x equals -1, and the minimum is -27 at x equals -3. So kind of like, why is this the candidates test? Notice how I never actually named that this is the candidates test, but this is the candidates test because what I'm establishing is where can my absolute extrema occur? They can occur at critical numbers, or they can occur at endpoints. So we find our critical numbers and justify how they are critical numbers, and then we test the endpoints, which we have here. And if we see, I doubt that this is still in my Desmos graph, but I can take a look at it. Yeah, it is not in my Desmos graph. So let's just go ahead and go back to the notes. All right, we can verify that graphically if we wanted to. Example number 2. Once again, what's our goal with this problem? Our goal is to find the absolute extrema. So what we did was we took the derivative and found the critical numbers of the derivatives. By the way, that's a minus. Critical numbers of the derivatives, and we know that they're critical numbers when f prime equals 0. F prime is not undefined anywhere because sine and cosine are both differentiable functions everywhere. So that would be pi over 4 and 5 pi over 4. So we established our 2 critical numbers, and then we established what are all my 2 endpoints. So I'm going to highlight these in red. And the smallest is the minimum, the largest is the maximum. Example number 3, same thing. So we do have to look at our interval, and if you see, we're evaluating and we're testing all of our values at the endpoints. And now we have as well critical numbers. So critical numbers, we have f prime, and f prime, once again, I use the calculator to come up with that derivative. It is useful for us to set it or put it all together as one fraction because where the numerator equals 0, so where the numerator, I'm going to change that, where the numerator equals 0 are some of our critical numbers. Where the denominator equals 0, that's where we have the undefined derivative. Undefined derivative. So in this case, x equals 0 does give us an undefined derivative, but it's not a critical number because, so if we plug in 0 to the original function, natural log of 0 doesn't exist. Also, we can't have the 0 in the denominator either. So 0 is not one of those values that we're going to work with. So where does the numerator equal 0? That happens at x equals z. So that's why I'm testing that value. And by the way, this is 1 over e. So we have our max value of 1 over e and our min value of 0. For number 4, take our derivative. Once again, I use the calculator for this. Set the numerator equal to 0. So when x equals -1, that's our critical number. Where does our denominator equal 0? Now, a lot of students like to multiply that out right away, and they're like, how am I supposed to figure out where this equals 0? Well, you don't actually have to because any number squared is either going to be 0 or positive. And then when you add 1, it forces it to be positive. Wow, I did not know that I could do that. Did not intend to do that, but kind of cool nonetheless. So as I was saying, our denominator is never going to equal 0. Therefore, the only critical numbers occur when the numerator equals 0, and then we evaluate at the endpoints, which I believe I had those shaded red. So add our 2 endpoints. Same thing here. This one I did a manual derivative on this just because personally I felt like it was going to be faster than typing it into the calculator. So set our first derivative, factored. And by the way, this is a good reason why I had you guys factor everything from chapter 1. So you wanted to, or sorry, not chapter 1, chapter 2. All of your derivatives were required to be factored because then I told you we were going to use them. And that was kind of the skill, and I wanted to push that skill during that time so that in chapter 3 we could focus on using the technology and then focus on the ideas as opposed to having to do all the manual derivatives. Can't lose that skill one more time, but we don't have a whole lot of time together, so I want to use it properly. So 3 to the x does never equal 0. So h prime is only going to equal 0 when x equals 0, and x is -2 divided by the natural log of 3. Which I have those here as part of my critical numbers. So unfortunately, I blew my color coding scheme because those were supposed to be the green. Hope you guys understand that. Let's just go ahead and have more fun with that and then make the endpoints tested. Our candidates test shows us that our max value is at the endpoint when x equals 1, and our min value is going to be 0 at x equals 0, so one of my critical numbers. Then I had some more work done with the Inspire, and I do apologize. I was trying to get the Inspire loaded on my computer, but it was not able to be done in time, but that's partially the reason why this video is a little late. I wasn't able to get it on here, so what I did was I helped them understand how to find the derivative in the Inspire, where I said, okay, we take the derivative of that function. So that to do the derivative, shift minus is going to be one of those keys for you. You say, okay, rather than go through all of the different menus, how do I come up with the derivative? Shift minus. And then once we get our answer, what we do with that answer is you start typing in the shift minus again, and then you can scroll up. And I wish I could show you this, guys, I really do. You could scroll up and then hit enter, and that'll drop inside the derivative. That way you can be more efficient in how you're doing your work. So anyway, what's the goal with our problem? I want to find the max value of f double prime of x. Find the max value of f double prime of x. First of all, I have to find f double prime of x, which is what I'm doing. When f double prime of x is x plus 2 over x plus 1 squared. Again, we use the calculator to find that. And then to find the max value, that means that we have to go and find the critical numbers, and we get those critical numbers from the third derivative. So I did have a student ask me in class, why would we ever want to do this? And my answer was, if the original function is position, the derivative is velocity, the derivative of that is acceleration. Is it possible I want to know what a maximum acceleration or a minimum acceleration is? And there's your answer. So in order for us to find the maximum acceleration and minimum acceleration, what we want to do is we want to find the derivative acceleration, critical numbers, and the derivative acceleration is jerk. So I want to find the maximum jerk. Big pun there, I apologize. So anyway, like before, endpoints and critical numbers. The critical numbers that occur, one of the things that you should notice, the critical numbers that occur do not actually exist on the domain. I didn't change this, or else I would have, but they don't exactly exist on the domain. Therefore, the only place where we're going to have our extrema are going to be at the endpoints. Then we also talked about 3.2 today. In 3.2, what I like about this is the two tie together where we say, okay, we have Rolle's theorem. And I'll get into Rolle's theorem in a little bit more specifics here, but I want to know what's the point of Rolle's theorem. The point of Rolle's theorem is I want to be guaranteed that f prime equals 0. So if we tie it back to what we just talked about, I'm going to say, okay, I want to be guaranteed I have critical numbers. If I don't have any critical numbers, then the endpoints are going to be my extrema. So I want to be guaranteed that I have critical numbers, meaning f prime equals 0. So to guarantee that I have critical numbers f prime equals 0, what I need is continuity on the closed interval and differentiability on the open interval. Now, a lot of students do question, why do we want differentiability on the open interval? And that's because if you look right here, what's the derivative of that endpoint? And the answer is you don't have a derivative at the endpoint. So the reason why you don't have a derivative at the endpoint has to do with the fact that the slope can be anything at that endpoint. We know what the slope is coming from the right side, but there's nothing coming from the left side, so that slope could be anything. So we take endpoints out of this, and Rolle's theorem is going to say, with the continuity on the closed interval and differentiability on the open interval, the last condition that we have to meet is that f of A has to equal f of B. The reason why that's important is because we need to establish, okay, this point here, and I'm zooming in. So these 2 points, if a function decreases, it has to increase back up to that point. And how's it going to do that? Through a slope of 0. So does it always have to go through a slope of 0? Well, in this case, if we increase and then decrease, if you notice, we don't go through a slope of 0. Rolle's theorem doesn't apply here. And what's going on is we lack the differentiability. So there is not differentiable at that point. So since we're not differentiable, there is no slope of 0. Yes, we do have a critical number, but I want to be guaranteed slopes of 0. So if we look at this one, our y value is 8 for both of those. I'm going to erase that. Y value is 8 for both of those. So polynomial functions, you should know that polynomial functions are continuous everywhere. So we want to say continuous from -2 to 2. And every polynomial is differentiable as well. In pre-calculus, I did have my students, or I always taught my students that every polynomial is both smooth and continuous. So smooth is a pre-calc way of saying differentiable. So going along with that, we now will say, okay, how can we guarantee that Rolle's theorem is going to apply? To be guaranteed that Rolle's theorem applies, what we need to do is check. So on the situation, do we have continuity on the closed interval? Well, what kind of function is it? This is a rational function. Rational functions are continuous everywhere except where the domain doesn't exist, which would be at -2, not on this interval, so I'm happy. So I know that f is continuous on that closed interval, and I know it's differentiable on the closed interval, sorry, open interval, followed by these two y values are the same. Therefore, Rolle's theorem applies. Now, in order to get to the conclusion of Rolle's theorem, we say f prime has to equal 0. So we found f prime of x right here. And we set f prime equal to 0. And what happens is I just threw the answer down here. How did I do that? Well, I used the inspire. As well as if you use solve, what I did was I put that answer equals 0, or I put that derivative equals 0, comma x in the inspire. That'll give us these two solutions, but only one of those is guaranteed, and that would be the positive solution. Example number 2. We sine and cosine, once again, are continuous everywhere and differentiable everywhere. Now f of 0 and f of pi over 2 are both 1. Since they are both 1, then I know that Rolle's theorem does apply. We take our derivative, set it equal to 0. And to solve this trig, I do bring sine to the other side, and then sine over cosine is 1. So theta has to be pi over 4. On example number 3 right here, we do not have continuity from -1 to 1. And the reason why I know that is because we know that tangent of pi over 2 is undefined because of the vertical asymptote. Well, that's when x equals 1/2. So since we don't have Rolle's theorem applying, we don't have to do anything with this problem, which is in some ways a big yay. I have had students who've done a lot of work and they solve this, and it's like, guys, please don't do that. Very first thing you should check is, does Rolle's theorem apply? And if it doesn't, you don't have to do anything. So once again, very, very happy that we don't have to do any work. Then we have mean value theorem. So kind of going back, summarizing one more time, what have we done? We want to know that where we have relative extrema, where relative extrema occur. They occur when the slope is 0 or undefined. Well, let's look at the slope of zeros because those are very, very beneficial and they show up quite a bit. So Rolle's theorem will apply with continuity and differentiability, and the y values are the same. But what happens if the y values aren't the same? Does anything special occur? Well, what we can do is look here and see, okay, I have the slope of a secant line. The slope of a secant line, the y values definitely are not the same. But if I have a secant slope, somewhere I'm going to have a tangent slope as long as I still have that differentiability and I have that continuity. So this is something special called the mean value theorem. So this is the 5th actual theorem that we're learning this year. So the mean value theorem, once again, do we have continuity on the closed interval, differentiability on the open interval? What we say is the average slope, so our average slope has to equal our instantaneous slope. So Rolle's theorem is really just a special case of the mean value theorem, where the slope is 0. And again, it has its purpose. We want to know critical numbers. We want to be guaranteed critical numbers. But the mean value theorem says, well, we can apply that to any slope, not just a slope of 0. So if we look at this situation, once again, we have a slope of 0. Let me take any 2 points. I'm going to randomly put 2 points here and say, okay, yes, I can find the slope in between those 2 points. And then if I draw any curve, and I need to make sure it's a differentiable curve, and I say, okay, where else do I have a same slope? Well, visually, I have the same slope there, right about there, right about there, and right about there. So in this case, I ended up with 4 separate places where I had the exact same slope, or exact same instantaneous slope as the average slope. So we're guaranteed this, and all that's required for that is continuity and differentiability. What's a real-life application of that? Let me jump to this right right away, where I say, okay, an application of this is two cars are 5 miles apart. Semi passes one traveling 50 miles an hour, passes the second one traveling 45 miles per hour. And it looks like that this semi is totally okay, especially if the posted speed is 60 miles per hour. However, the officer pulls the semi over. And the reason for it is because they're 5 miles apart and it was 4 minutes later that they passed the second one. So what we're looking at is what is the average speed of the semi truck? That average speed is 75 miles per hour. We did a little bit of dimensional analysis here. So if the average speed of the truck is 75, it's kind of common sense that says, okay, if the average is 75, therefore at some point you have to be going 75 to average 75. And most likely you're going to be going well over 75 if that's going to be your average. So you can, or the cop couldn't be justified in giving the semi driver a ticket because their average speed had to have, or their instantaneous speed had to have met their average speed at some point. So how do we test it on some functions? To test on some functions, what we do is, once again, we check, do we have continuity? Do we have differentiability? So therefore, mean value theorem applies. It almost looks like MNT. Let me write that a little bit clearer, MVT. Okay. So since we have that, what you'll see, and I'm going to try to be consistent here and say, okay, this right here is my average slope of -1/2. I take the derivative, and I'll do the derivative in red. There's my derivative. Set my derivative equal to my average slope. To say, where does my instantaneous slope equal my average slope? And to solve for c, we get plus or minus square root of 2, but only the positive square root of 2 is on that interval. Example number 5, very, very happy. One of the things that if you try to find f of 2 and f of -2, you'll get the same y value, so it almost looks like Rolle's theorem applies here. But just keep in mind that you cannot take the square of a negative, so the domain does not exist. So does not exist on parentheses, -1 to 1. And then for this one, do we have continuity? Yes, we do. Do we have differentiability? Yes, we do. So therefore, mean value theorem applies. This is my first derivative. My first derivative, I set it equal to the average, which I told you I was going to be doing that in blue. So there's my average slope. The red is my instantaneous slope. Set them equal to each other and solve. Now I did end up, when I solved, I had a couple different cases where like, or it's just not on the interval. So the only one that's on the interval is pi over 3. And then we had some multiple choice problems. When it came to the multiple choice problems, what I looked at, I hopefully gave enough information. I'm debating right now whether I go through each problem. One of the things that I do look for is like terminology. So f of a equals f of b equals 1. To me, that shouts out that we have Rolle's theorem. Something that's kind of hidden here is we have a polynomial function, which implies that we have continuity and differentiability. So what all has to be true? F prime has to equal 0 by Rolle's theorem. We can look at all the other individual cases, but we're not guaranteed that the function value equals 0, because if I have a second degree polynomial, so if I have a second, I guess I do have this drawn out here, I'm not guaranteed that I have a 0 in between. I'm also not guaranteed that the second derivative is 0. Now, if the second derivative is 0, this is kind of like jumping ahead a little bit, but if the second derivative is 0, that means that we have a point of inflection somewhere in between. There's no point of inflection, so we're not guaranteed it. For the second one, continuity on the closed interval, we have continuity on the closed interval. Then g of 0 is 1, g of 1 is 0. I kind of drew in my situation here just to kind of get an idea. Then I realized I didn't need to do that because this problem is all theoretical. So the first one, there exists a number such that g of x is greater than or equal to, or g of h is greater than or equal to g of x. To me, that shouted out extreme value theorem. And does the extreme value theorem apply? Well, do we have continuity on the closed interval? Yes, it does. The second one, for all a and b from 0 to 1, if a equals b, meaning that it's only one number, does g of a equal g of b? Yes, we have a function, therefore that's true. Do we have a number from 0 to 1 such that g of h equals 1/2? I guess this is where, do we have to have a y value of 1/2 here? Yes, and that's by your intermediate value theorem. For D, g of h equals 3/2. Well, 3/2 is up here, so we're not guaranteed that. So D is our answer. But this last one is our definition of continuity. One of the things I really like about this problem is it brings back a lot of our theorems all in one problem. For AP2, you'll see this a lot in terminology. Find all values of C satisfying the conclusion in the mean value theorem. So what's the mean value theorem? Our derivative equals our average slope. Well, what is our average slope? It just occurs to me I might not really have the right answer on here. So what's my average slope? What is f of 3 minus f of 0 over 3 minus 0? F of 3 would be 27 minus 27, so, which is 0. F of 0 is 0 over 3 minus 0. So we do want this to equal 0. So thankfully, I'm actually right. So I got a little bit lucky on that one. Yay. How about AP4? Once again, satisfying the conclusion of the mean value theorem. So we have to check, is sine a continuous and differentiable function? The answer is yes. Therefore, mean value theorem applies. And just to show continuity differentiability. Okay. Continuity on the closed interval, pi over 2 to 3 pi over 2. Differentiability on the open interval, pi over 2 to 3 pi over 2. I can't just let that go. Then we say our derivative of sine of x over 2 has to equal our average slope, which that derivative does equal the average slope if we kind of follow through the solving at x equals pi. Therefore, that is our answer. Hopefully you gained a lot from this today, and I look forward to working with you in the future. Take care, Calc students.